data created through these online interactions and social exchanges. The real question I'm going to try to be investigating here is, what is the value of integrating geo and social together? What new types of questions can we answer? And does it matter for social sciences research? In terms of the kind of different applications of creating geographic data on the web, from structured data on the left hand there where we have things that are mapping the physical environment like OpenStreetMaps, all the way to geocoded social media posts, which I'm going to focus on. And perhaps the types of questions that we can ask and answer differ with respect to where we are in that paradigm. The second kind of basis for this is spatial analysis and spatial pattern analysis. So the idea that we have these processes operating across space and through time. And if we look at the resultant spatial patterns of those processes, we can learn something about the underlying generating processes, and particularly about the relation of events to the social and environmental context. We've heard a lot about context today and how it's important for social media data to look at it in relation to its context. And in geography and spatial analysis, we're really interested in using GIS as a way to use space to integrate data, right? So obtain data from all these different sources, extract the spatial reference, and then use space as the index to bind data together and look at relationships and associations and ask new types of questions. And I think this is more doable now because we have more data that's open, more accessible APIs, and lots of GPS sensors and low-cost ways to collect spatial information. As I get into this sort of work, I end up navigating into fields like natural language processing and computational linguistics, because getting the value out of geosocial data is not as easy as having a nice set of columns with integers that you can create a histogram and the things that I'm kind of used to doing. And so I think as social scientists, we get into these new types of fields and accessing these new types of data, there's a whole new set of tools that we have to learn. Everything from decoding the meaning in text references. I'm particularly interested in pulling out geographic or spatial references and temporal references and looking at those in terms of spatial relationships and evolution over time. And this idea of disambiguation, how do we tell the kiwi that's referenced, whether it's the fruit or the flightless bird or a person who happens to be from New Zealand. Classic problems to many that have been in this field for a long time. But as we're applying this in new ways, we're running into addressing these research challenges. I'm going to give two examples. The first is understanding urban place. So the idea that places are kind of different from looking at space, because place implies the human, right? So space with meaning, not just looking at spatial coordinates, but the experience of people in the urban environment. And this might particularly be an interesting way of looking at what geosocial can do, right? So having the social element binded with the spatial to answer questions about how people experience their environments, from the idealized kind of urban space before it's developed to what it's like when you're there and you get that sense of place. We started to look at this through geotag photographs. I kind of removed all my slides that talked about how we did that, just obtaining data from the Flickr API for the city of Toronto. And here's an example of a problem looking, so a quick search for cats in Toronto. We have my gal likes her teens, wait, I must too, hashtag cat, hashtag ritual, versus the Thai cats versus the production cats. So deconstructing these references to fit our research needs is an important challenge that is part of this work. Our objectives were to develop methods to explore urban space, explore specifically how spatial and semantic similarity can be used together to understand what this data can tell us about urban places. And then particularly look at areas of agreement and disagreement. And I'll talk about what I mean by that. The study area for this was the city of Vancouver for a host of reasons there that are kind of difficult to read, but the best reason is that's where I'm from, so I kind of have a good handle on the different regions of the city. So in terms of having the geosocial data for geotag photographs, We aggregated Flickr over using hexagonal aggregations that were mentioned earlier. We really wanted to look at, because aggregation of data is something that we kind of do and don't think too much about it. In geography, we're all obsessed with scale. So we wanted to do this over multiple spatial scales and kind of see what changes with scale and what stays consistent with scale. So we did this for different scale hex combinations and basically pulled out the top 10 most frequently occurring tags and had a tag count, and then looked to basically answer the question, are people tagging things the same way that I am in my local neighborhood? So in terms of a spatial neighborhood, hexagons that are surrounding every given hex, look at the proportion of tags in each hex compared to the proportions tagging things in the neighboring hexes. So I had a formula up there, but I decided to get rid of it and just focus on the maps. What we found, the first result is not surprising. So we have hexagon size or spatial scale of aggregation on the X, and the average similarity, log odd similarity. So the likelihood that you'll have similar tagging among spatial neighbors on the Y. So as you aggregate up, the dominant tags become are the same across spatial variations. And so there's less interesting things to look at when you're very spatially aggregated, right? Because the top 10 tags are all Vancouver, coast, it's raining, things like that. What is more interesting is you start to drill down into different levels of aggregation. So we can kind of see, I'm going to try the laser here. We can think of this as tag sets that are tagging similar to neighbors and then dissimilar in the blue and red. And so this is the Gastown area of Vancouver, downtown east side, and Chinatown, and broad areas of agreement in yellow. And then as we move down into lower spatial scales, we see that agreement break out into disagreement as tags are more unique to the local area. Even further, and then we can start to unpack what it means and what the differences are in terms of how people are characterizing those environments. Also looked at doing multi-scale analysis, so looking at areas of agreement across spatial scales through transparencies. And the take-home really was that looking at tag frequencies is pretty boring when you're looking at the dominant trends, right? People are saying it's Vancouver. And coming at it from my background, I'm used to looking for central tendencies, central patterns. And really the value here is in the individual and unique references rather than the general. So we get down to the local level and look at, I think this is 1 hectare scale and quarter hectare scale. We see areas of kind of agreement break out into disagreement, and we see references to addiction in the downtown east side and poverty. And there was Jay Black, who is the photographer who's doing a protest campaign around homelessness in the Olympics at the time, popped out as a significantly different from neighborhoods. So those types of things are really what's interesting, I think, in analyzing this data. So this idea of looking at the local scale, but within the context that's been mentioned before, I think is very powerful. The next bit that I will get to is looking at geospatial dimensions of emotional expression. So what can we extract from geosocial data in terms of the emotional content of messages, specifically in Twitter in this example. We were working with a team in the UK who's developed an ontology for extracting emotional content from tweets into an ontology of 8 basic emotions. Often with me, when I'm working with big data, it's basically frustration, which isn't there, but sometimes confusion and sometimes anger. So for this, we're extracting tweets from the Twitter API, decoding the emotions, and looking at spatial variation across the city. And for this, we're using Toronto. The objectives of this is very exploratory, first cut at this sort of work, to develop a kind of conceptual framework for looking at individual contextual relationships of tweets, and specifically the geographical and spatial relationships. And to develop the computational tools to look at these expressions and to kind of develop this idea of the urban emotional fabric, how it varies over space and through time, where is there consistent expressions of emotion, where does it change? Is the park a happy place all day? Does it change to a scary place at night? That sort of experience of a place, which I think you can do with this sort of data, we're hoping that we can start to get at. So my first cut at this was late at night a few nights ago, and I thought I'd just characterize the percentage of positive tweets. So extracted tweets from 5 days this year. I can't remember how many there were, maybe 100,000, and aggregated to City of Toronto neighborhoods. And so, you know, one naive method might be to say these areas are happier than the green areas, but that could also be related to the number there, like unstable ratios based on the denominator, right? So I thought I would standardize positive to negative. And so areas that are light green might be neutral. Areas that popped out as significantly happy, I was very excited to see that this is Mount Pleasant East and Pleasant View. So just you might expect that there would be the happier place, and maybe not so much on the west coast of this west part of the city. When we see patterns and we do spatial epidemiology, that my kind of background, we always want to validate and look for statistical significance. What's the p-values or real effect? So I ran a spatial scan statistic analysis to identify statistically significant, the most powerful cluster of happiness, if you will, in the city of Toronto. So this would be the happy cluster for the city of Toronto. We can see the p-value is very low. Normally that would make me very happy because it would suggest that it's a significant effect. I took a look at the area in Google Earth, and it looks like there's lots of parks, so it looks like a happy place to be. There's people riding bikes, and it's leafy and wonderful. One of the implicit parameters of that method is the population at risk. So how big what's the maximum size of a cluster? So if I change that to 5 kilometers, then these two areas pop out as significant. And they both have low p-values, generally under the accepted alpha. They might be accepted as, yes, this is a significant effect if this was an actual disease cluster investigation, not a cluster investigation of Twitter happiness. And I took a look in particular at the one on the right because it seemed a little weird, and this is what the data actually looked like. So this is the distribution of tweets. There's around 26. And it looked a little odd to me, and they're basically 2 people staying in the same location, having a conversation back and forth. And there are actually references to happy birthday just embedded in these tweets that are given by 2 people there. And that's a mistake, and I thought, you know, maybe I'm doing something wrong, and I saw this paper just last night, the benefit of doing a talk late in your hotel room the night before. So this is published in Science, and it's talking about the Google flu algorithm and how it's been off track for the last couple of years, to the point where they overestimated the influenza-like illness peak by more than double using Google's tried and tested algorithms. And the explanation for this error, for this modeling error based on big data, was that the Google algorithm search team was changing the algorithm in a way that might direct people to buy different prescriptions and things for illnesses, and that the Google flu team was in the other wing of the building, and they're picking up people going down that click path and basically not talking to each other. So when people were changing the algorithm, they're picking that up and saying, oh, there's going to be an outbreak of flu. So it goes to show you have to be careful working with this sort of big data. This is a really interesting article I encourage you to check out. So in summary, the data processing, I think, is increasingly the analysis rather than trying to do statistical significance and apply models to things. Visualization over statistical significance and models is certainly more powerful in my initial cursory explorations into this. And I still think that the opportunities in terms of geosocial do outweigh the challenges, and there's a lot of real opportunity for interdisciplinary work to kind of come together and share skills with this. So I'd like to thank the following people and organizations for help of different sorts. And I couldn't decide on what message to leave you guys with, so I left 2 up there. And thanks for your attention.
I wonder how universities map onto your happy dots there. Okay, our next speaker is Andriy Shkilko from Laurier. And Andriy is in finance and is interested in securities trading and is going to talk about finance and big data.
Good afternoon, everyone. I guess we just almost transitioned into the afternoon. Thank you, Andriy, for the opportunity to speak about my experiences with big data, and also wanted to thank Dominic for his earlier introduction to finance. If you remember earlier this morning, Dominic mentioned finance as part of economics as one of those fields of science that gets away with anything, which is perhaps partly true. But I was sitting back there and I thought to myself, well, this actually makes it easier for me because the expectations have now been lowered. So here we go. I was hoping to talk to you guys about market structure research to sort of introduce you to our issues with big data, and our data are pretty big. So before I go into this, I wanted to make sure that everybody is on the same page as far as what market structure research actually does. What we do is we study securities markets, or rather, I should probably call them asset markets. And if you're not sure which markets I am talking about, which you probably shouldn't be because there are several definitions of what a financial market is, I'm predominantly talking about stock exchanges here. There are other exchanges out there. There are bond exchanges. There are derivatives markets, currency markets. All of this we are trying to understand and are trying to make sure that it functions properly. But our main focus is on stock markets just because there is more information about them out there than about the rest of the field. So our main goal in market structure research is to understand how markets work, why they work the way they do, why they sometimes malfunction, and how to make them better. And by better, I mean more fair, more equitable, how to make them provide better liquidity and better price efficiency. And I know that not all of us like thinking about the money, and financial markets is all about the money. But I think I don't need to remind you that all of our retirement assets are being circulated in those markets. Your kids' college funds are there. Basically, for us to have functioning financial markets, very important for us to have financial stability. So I know that I have given you a very bookish definition of what financial markets are and what market structure is trying to do about them. So I was hoping to give you two examples about how market structure research actually helps making our markets better. And I was hoping to start with a historical example. So back in the 1990s, there was a very famous series of articles in market structure where two of my very esteemed colleagues, Bill Christie and Paul Schultz, found that there was quite a bit of collusion, and I don't want to use the word fraud, but a lot of people would qualify it as fraud, going on in our financial markets, in a sense that dealers, folks that are out there in these financial markets trying to provide liquidity, were overcharging their customers. If you want to ask me how much they were overcharging their customers, I'd probably say they were charging double of what they should have been charging in a competitive environment. If you would ask me how much money we as investors lost as a result of this collusive behavior, I'd say it's probably in the tens of billions of dollars, although no one has ever been able to quantify this. So by using data and data only, without wiretapping anyone's phones, without infiltrating anyone's dealerships, Christie and Schultz were actually able to show and prove that this kind of collusion was happening, and then the government got involved. The naughty parties were fined a couple of billion, not necessarily the tens of billions that I mentioned earlier, but anyway. And our markets underwent a significant overhaul and supposedly got better. Actually, new research shows that they did get better back then. Unfortunately, or maybe fortunately for us, our markets are extremely dynamic. They evolve and change faster than we can actually analyze them, which is one of the burdens of market structure research. So since then, since we thought that we had fixed our markets kind of have outsmarted us quite a few times. Not to dwell on history too much, I am going to switch over to my second example, which is what our markets are dealing with now. Those of you who are following this kind of stuff probably have heard that we have had quite a bit of a paradigm shift in how trading happens in our securities markets. Some of you may remember pictures like this from just a few decades ago, really, when our financial markets looked like large crowded rooms with a bunch of people shouting at each other, trying to trade with each other. There was a ton of paper flying around. That's how financial transactions were happening. Well, our markets don't look like that anymore. In fact, most of our securities exchanges have closed their physical trading floors. In North America, the only decent floor that remains is the New York Stock Exchange, which is on the right side of this picture. And you can probably tell from the picture it's not really crowded, right? It's mainly computer screens. There are a few specialists standing around there. Most of them are probably chatting about life for most of the day. So then the question that you might want to ask me is, well, what's happening? Are we trading less now? Well, this is actually exactly the opposite of what's happening. We're trading way more now than we used to. So this timeline here shows you trading volumes from 1926 up till just a few years ago, so up till 2012. And you can probably tell that we trade way more now than we did just in the 1990s. In the 1990s, in an average month, we would transact about 7 billion shares in our North American markets. Now the count is into 150 billion shares, and perhaps growing even more. So then the question you might ask me is, well, if our markets are quite calm, or at least they look calm, where is all this volume comes from? And that's where. So trading these days is extremely computerized. There's almost no human involvement there anymore. I mean, humans write algorithms that tell these machines how to trade, but the trading itself is done by machines. And these are very fascinating machines. They're extremely fast. The algorithms that are loaded into them can make decisions extremely fast, within nanoseconds. And because our markets are so fast these days, the location of these machines is actually very important. In other words, it's not enough for me to have a trading computer in my office in Waterloo and try to trade on the New York Stock Exchange or in the Toronto Stock Exchange, because there are machines that are trying to trade the same assets that are located 1 meter away from the exchange server. And that distance, the distance between Waterloo and 1 meter away from the exchange server, matters a lot now, because trading is in nanoseconds. So the speed of light matters. So you can probably imagine that these machines that trade in nanosecond intervals produce a lot of data, which brings us to the big data. So I wanted to give you just one example real quick of what kind of data we usually see when we start looking at the stock market. So this is 4 seconds of trading in one stock a year ago. And the stock, if you care, the stock is Semantic. It's a software company that some of you probably know for their antivirus software. So if you look at these 4 seconds, you'll probably see that there were close to 12,000, oh, by the way, I should have probably told you that every little colorful tick on this picture represents an order. In other words, there's a message generated by one of those super fast computers that goes to the exchange server, and they're trying to communicate with each other. So if you start counting these, and I don't encourage you to, but anyway, you'll probably see that there are about 12,000 of these orders that are submitted within these 4 seconds. These orders resulted in about 1,600 trades, again, within the 4 seconds, and this was about 500,000 shares of Semantic changing hands. Now, I do have to admit that I chose a colorful example. This doesn't happen every second of every day, but this happens a lot, and we in market structure research have to learn how to deal with this. And of course, as I mentioned earlier, this generates quite a bit of a volume of data for us. So what kind of volumes are we talking about? So no one does this kind of research on purpose. So I actually had to go to 2011 calculations on how large market data are these days. But one of our consulting firms, Celent, did a calculation for 2011, and they figured that global market data for 2011 was about 2 zettabytes. Now, until I read this article, I didn't know what a zettabyte was. It's actually a sextillion of bytes. I'm not sure if you know what that means and how large that is. I actually don't know how large that is, but what I do know is that it's extremely difficult to work with this kind of stuff, with these kind of volumes. So what do we do so that we can actually still make some sort of conclusions and decisions on what's going on in our financial markets? Well, we reduce the size of these data sets quite a bit. How do we do that? Well, first of all, we select which market we focus on. I mentioned earlier that personally I work with the equity markets for the most part. Some of us choose to work with derivatives markets. That sort of reduces the size of our data from zettabytes into something more workable, like terabytes. So what else do we do? Well, we look at relatively small time periods. A common market structure study would probably look at several months of data. And we often get ridiculed by our finance colleagues who sit just a couple of doors down the hall from us, because they tell us that they take weeks to analyze years of data, and we take years to analyze weeks of data. Well, what can we do? So we try to focus on relatively short time periods. We also try to focus on relatively small samples of assets, let's say, or stocks in my case. Most of my studies, for example, are around 150 stocks. That's out of thousands of stocks that are listed out there, and this is something we have to do, and we try to make these samples representative, or as representative as we can convince ourselves that they are. We also we also use specialized software. I'm going to talk about software that we have to use in a minute. Not all statistical packages that are popular in finance, unfortunately, can deal with these large data sets that we're working with. So we're pretty restricted there. And then using the software, we actually try to, and I have to say try to because not all of us are very successful, write efficient code. And it's very important with these kinds of data sizes to write an efficient code, because if your code is inefficient, you may actually add a month to your processing time, which none of us wants because we're still under tenure pressure and all of those other wonderful things. And we, of course, have started recently using, and this is a big breakthrough that we're very happy about, we started using parallel processing, and I'm going to talk about that in a few minutes as well. Just to give you an example of how this reduction in data sizes actually works for us. Again, no one works with 2 zettabytes. No one dares to. And actually, I forgot to tell you earlier in this slide that this is the 2011 data, and the same consulting firm actually projects that this data, the global market data size is actually going to double every year. So now we're probably somewhere around 8 zettabytes. So, of course, we don't work with that. The usual data size that we work with is about 2 terabytes, which is actually workable with on our own computers in our offices. But we're still struggling a little bit because our data are very raw. When we get it, it's very raw, and we have to create additional variables, and a lot of them. And those additional variables, when added to the data set, of course, increase its size. So we are struggling a little bit there, which goes back to trying to write efficient code. So what are our challenges? Since this is supposed to help policymakers make decisions, what are our challenges? Our data are getting larger every year. And unfortunately, we really can't store it on every university's level. So we have to rely on some sort of silos that were mentioned earlier today. And our most favorite silo is the University of Pennsylvania's Wharton Research Data Services database. It basically takes all those terabytes or whatever they are of data and allows us access to them, but not for free. So they're a non-for-profit organization, so I think they're not trying to make money off of this, but they still charge us to access these data, and the charge is about $10,000 per year. And this is just to access the data. This is not to purchase the data. We actually have to purchase the data too. So our costs of doing this are pretty high. Depending on the data set, you're paying $2,000 for the data set to $30,000 for the data set, plus $10,000 a year for processing. So this adds up, and we're very thankful for the Tri-Council funding, particularly SHRC funding for us. A bit of a challenge that we have been running into is that some funding agencies, such as, for example, Canada Foundation for Innovation, are not necessarily happy with data purchases, right? We have to kind of convince them that we're not purchasing pre-processed data, rather we're purchasing raw data. Sometimes this presents a challenge for us. And finally, our hardware issues. We churn tons of data through our computers on a regular basis. Basically, our hard drives never stop spinning. And, well, now that we have solid-state drives, I guess whatever they do. This results in a lot of wear and tear, unfortunately. I just last week went through a hard drive failure number 100 and something. And this is quite a bit of an annoyance for us. So this is a bit of a challenge, and we, of course, encounter additional costs because of that. So that's unfortunate. Another challenge for us is the statistical software. As I mentioned earlier, there are preferred statistical packages in finance and economics in general that allow us to do our econometric analyses. And some of these packages are more user-friendly, and they're a little bit more sophisticated than others. Unfortunately, those that are more user-friendly and more sophisticated cannot work with large data sets. For example, if any of you work with Stata, you know that it's a pretty good statistical package, but when it comes to large data sets, it's pretty useless. So we have to rely on other software, such as SAS, for example. And a bit of a problem with SAS is that sophisticated statistics are not as straightforward there as they are in Stata. So a bit of a challenge for us there. And another thing I mentioned earlier, that we are trying to make use of parallel processing, particularly the online application of it, such as Amazon Web Services, where you can submit your jobs to Amazon's cloud and it will do the computations for you. This significantly speeds up our data processing. For example, what I would be doing for 2 months on my machines in the office will probably take a few minutes if I sort of get access to enough CPUs on Amazon. The problem is that our statistical software has to be licensed to every CPU. A license is about $100 per CPU, so you start multiplying it by 100 or by 1,000, and you quickly run out of your research budget. So something that we're still working on. We have actually been switching to open source statistical software so that we can use it on these kind of cloud computing arrangements. It's a bit of a painful transition, as you can probably imagine. if you're used to a particular package, you really don't want to, unless you're forced to switch to another one. I know I've complained a lot about how large our data are. Let me now complain about not having enough of it. We actually have a ton of data, as I mentioned earlier, but unfortunately we don't have the data that we really, really want. For example, we were trying to understand how financial firms make decisions and why they make decisions the way they do. Of course, financial firms don't really want us to understand how they make decisions, and particularly why, because that's their proprietary information. They're making money off of it. So for us to truly understand markets, we would actually benefit from some truly detailed information. Unfortunately, the information we're getting, although it's very large, is relatively superficial. So there is still a very long way for us to go trying to understand how all of this works, and I'm not going to go into too much detail on this. And finally, the organizational challenges. So because it takes so long for us to get the result that other folks probably don't need to wait for that long, it's very difficult to attract PhD students to this particular area. Because again, my colleague next door will tell them, well, you will probably write your paper in a year. And I will tell you, well, you'll probably be done with the first step of data analysis in a year. And it's basically a non-brainer for most students. So it's quite a bit of a challenge to attract them, but still, I thank my students, if they're watching this on YouTube, for working with me. And of course, from these longer data processing times, there come challenges when it comes to funding, awards, and things like that, because people often compare lists of publications. And again, even in finance, folks in different subdisciplines of finance can actually publish faster than some of us who work with larger data sets. Having said that, there are a ton of opportunities in this field, and I wanted to end on this relatively exciting note. As I mentioned earlier, markets are constantly changing. Some of my colleagues actually compare our markets to a smart virus, in the sense that you kind of figure out how to fix it or how to make it better, but it's smart and it knows that it will make money if it kind of circumvents whatever regulations you've created for it. So it actually does that very quickly, and then you sort of get into a new research project trying to understand what to do with this new development in markets. So we never really run out of things to do. And luckily for us, we have been attracting quite a few folks to PhD programs with computer science backgrounds, which makes it quite a bit easier for us in terms of data processing, especially with the new volumes of data. So we are very happy about that. And finally, I'm very happy to report that our governments, particularly the Canadian government and the Ontario government, has been extremely forthcoming about giving us new data sources and providing funding for this kind of research, because they understand how important it is to have our markets in a stable state rather than states that they can sometimes achieve. Having said that, thank you very much for the invitation to speak here. Thank you.
Very nice treatment of not only the technological and software challenges, but the budgetary challenges, of course, of doing transforming over to big data research. So our last paper of the morning is our visitor from Guelph. Susan Brown is from the School of Arts at Guelph, and she specializes in women's writing, Victorian writing, and digital humanities.
Well, thank you. I realize I stand between you and lunch and a delayed schedule, so I'm going to try to go as quickly as I can in talking about this particular web. And this work is in connection with work by John Simpson and with the Text Mining and Visualization for Digital Literary History project, of which Mike Bauer is a co-applicant, and also with the Implementing New Knowledge Environments projects. And I'm taking this occasion to think big. I was given a rather big slot, although I'll see whether I can speed things up a little bit. So there's some pretty broad brushstrokes in what follows here. I take my title. Down here. Can you hear me? Yeah, okay. I take my title from the Victorian novelist George Eliot, who in writing Middlemarch as a belated historian, sensitive to the changing conditions of both history and historiography, articulated the need to focus on a particular web. She articulates simultaneously the importance of particularities and the interrelatedness or relevance of everything else to the matter at hand. She also invokes the potential breadth of the data related to cultural inquiry as basically everything in the universe. So Ian Milligan and I have somewhat similar challenges, I suppose. This holds whether we consider culture rather narrowly, in the words of Matthew Arnold, as the best that has been thought and said, which has to be thought of course, relative to the rest, or more capaciously, as defined by Raymond Williams, as the record of human thought and experience, or the embodiment of a particular way of life, in everything ranging from art to ordinary daily behavior. And while Eliot asserts the need to focus, students will be the first to tell you that for her, this particular web was rather big. It took her 800 pages to detail and investigate, among other things, the changing flows of information that characterized the historical shift into what we now know as the Victorian era. The web we contend with, as we're all aware at this point in the day, exceeds Eliot's particular web exponentially, unimaginably, and narrative may not be the best choice for engaging with it most of the time. But what I do want to argue is that, tempting as the range of relevancies that make up the digital universe are, we too must retain the ability to shine light on particular webs. So, quick overview. I'm going to talk about the potential of big data for cultural inquiry, and I'm really focusing on the needs of mainstream scholars, not those of us who've sort of specialized and learned how to program, but how this could change the field. I'm going to give an overview of the state of the semantic web in relation to digital humanities work and more general linked open data, and then talk about where we need to go. My perspective here emerges from a lot of collaborative work with a number of people, including Ruth Knechtel, who's here today, who was, until quite recently, the project manager on an infrastructure project that I'll touch on briefly. So, humanities research interest in big data is growing. The engagement with archives beyond the scale of normal humanities research methods has been taking off in a lot of ways. This work is phenomenal. It's groundbreaking. It has the potential in many ways to shift the discourse of our discipline. It's generated a lot of debate. I wouldn't say it's had a lot of impact on practice. That's because it is easy to engage with theoretically in the abstract. It's easy to talk about what it means methodologically. It's hard for most of us to engage with practically without mounting projects of a similar scale. The results are irreproducible. They're not testable. We have no access to the data. In many cases, we're actually left with less evidence to judge an argument on than we were with traditional research methods when we could look at the text that was involved. So the potential of semantic web data, and that's where my focus is going to be on today, is that it's designed to get it, to retain particulars, to get at particulars, to make them machine processable so that new kinds of light can be shed on them. It's designed to be flexible, and this is important within the area of cultural inquiry, where there's so many different approaches and areas of interest that we're not going to be able to sort of standardize methodologically the way that some other fields may. The semantic web is designed for interoperability and granularity to overcome silos, which we've been talking a lot about already today. And it offers the promise of powerful reasoning and inferencing. When put on the web, it becomes linked open data, and since this is the kind of semantic web data that we need for this area of work, I'm going to use those two terms interchangeably, although I know they're not the same. So I'm just going to romp really quickly through RDF, defined by Tim Berners-Lee in 2001. It relies on the idea of triples, which are very attractive to humanities scholars because they're grammatical. They're a subject, verb, and object in machine-readable form, which can be translated into more straightforward human-readable form very easily. And when combined with other triples and combined with ontologies that give you information about the relationships between the components of a knowledge set, can lead to inferencing. So Joy Kagawa is, of course, a Canadian writer, but she's not just or simply a Canadian writer. She's also ethnically Japanese, and her writing is bound up with what it means to inhabit a hybrid identity. So hybrid and hyphenated properties of the kind that Kagawa invites indicate how quickly even simple assertions and categories can become, in a cultural context, committed to specificity and the tracking of difference, much more complex. So we do have the semantic web in action This is the way it's impacting most of my colleagues right now, is through the knowledge graph and the right hand of Google search results pages. And it's quite a nice graph that we get for Kagawa. It represents her as a poet. I would call her a novelist first, but that's quibbling, I think. And gives her relationships to other people. The relationships, when we're thinking about the hybridity of her identity, emerge most clearly in the people who are also searched for. That's not, I think, the result of semantic web data. That's the result of leveraging search behavior. So the semantic web is not quite there yet, but it still is a pretty rich set of results. We also get a nice set of results for Pauline Johnson, who also comes from a hyphenated or hybrid ethnic identity. And at the bottom, you'll see the graph is actually able to specify relations to a couple of the people who are associated with her, which is nice. That's the sort of thing we hope to get from the semantic web eventually, is the specificity of relationships. But we could compare that to another graph. This is generated from an interactive visualization tool produced with SharkNet funding, thank you to SharkNet, and in collaboration with Mike, to visualize with a standard graph the relationships between people in a research project that I direct on literary history called the Orlando Project. So here we see a set of relationships, and they're color-coded by type, and those types range from Milton, for instance, is an educational text, relationships having to do with race and ethnicity, friendship, intertextuality, fictionalization, literary reception, and so on. So this is siloed data. It's not open, although it's going to become open. We're extracting, this is actually generated from XML, but we're using that XML as the basis for generating triples, which we're pushing out as open data. And so the challenge will be, how can we bring this kind of data into dialogue with other data sets so that they can enrich each other and enable the kind of big data analysis that we'd like to engage with. What we want to do is be able to bring together lots of different materials into an organized, semantically meaningful set of materials of the kind that always get gathered by things like Google search, but that we don't understand the relationship between with any ease. And then if we can scale that up, then we can start to make sense of what those relationships are overall. So my two examples that I've used here are border cases. They have in common that hybridity or marginal subjectivity, and yet they achieve some kind of cultural centrality. They're representative of one of the sorts of particularities that cultural inquiry wants to get at and make sense of. They are, in some sense, the long tail that's essential to an understanding of culture and how it works, not least because there's a strong association between marginality, liminality, border crossing, and cultural creativity. So that brings us to the paradoxical insight articulated by Matt Kirschenbaum, and interestingly just articulated here in relation to economic data, that when it comes, to geographic data, that when it comes to text mining, what we're looking for is not the dominant, but the stuff that can be hard to get at, because it might look like noise in the system. So how can we get to what Alan Liu calls the kinds of humanistic phenomena that appear only at scale? How do we get past the million books problem now that we've reached the point where we can't humanly engage with our old methods without losing that ability to get at diversity? So I want to turn now to the semantic web. It's been growing exponentially. The CCAN Data Hub had 12 open link data sets in 2007, 295 in 2011, and yesterday 9,093. So I don't think we yet have a killer app that uses semantic web technologies. It's being used in fields more and more widely for things like cancer research, as well as information retrieval in search engines and lots of other areas too. So to look very quickly at what digital humanists are doing with the semantic web, we have three prominent types of projects. Domain-centric projects are extending essentially existing cataloging and archival practices, but using RDF to do that. Museums, archives, and libraries have been very prominent players in creating online repositories, some of them very large, using RDF as a metadata format. But they still tend to be siloed. They still don't interact well. It's hard to do more than use them for discovery, which is what they were designed to support. There's an increasing body of tools. Not all of these have been developed solely for the digital humanities community, but they all have some DH involvement in them. And these are focused largely on resource enhancement or creation, not focused so much on using the logical structures of ontologies, for instance, to enhance algorithm-driven discovery or inferencing. And finally, aggregator projects, which are pulling together similar collections from disparate sites to create a single point of access or portal from heterogeneous and scattered materials. So I want to focus for a moment on one of these, which is NINES, the Networked Infrastructure for 19th Century Electronic Scholarship. I think one of the showpiece projects in my field of Victorian studies. It aggregates close to 1 million objects. And its sister project, ARC, is pulling in parallel sites for other fields. So we're going to end up with the ability to search across periods, across millions of objects, with a combination of metadata managed through RDF and full text searching. So it's a relatively lightweight application of RDF that's had a huge payoff. And if we look at the snippets of search results for Pauline Johnson here, we can see 3 types of data aggregated. One is from the Orlando project, a Cambridge University Press database, another the Alexander Street Press. And so there's quite a number of commercial publishers with paywalls, but they've exposed their data to the search engine so that you get much better results than through searching through normal journal indexing services, for instance, if you're looking for somebody who wouldn't come up in the metadata because they're not significant enough to merit a metadata term in the cataloging, but they do get mentioned in the course of an article. And finally, the most interesting one here, I think, is a born digital humanities collection called Collective Biographies of Women, which is essentially a research archive that was produced by the scholar Alison Booth, who published a major book on this topic with the University of Chicago Press, and she just digitized all her research archive. So you get essentially her card catalog with all her idiosyncratic notes, her coding, but it's an extremely rich resource. And it's the type of knowledge that currently sits on scholars' hard drives, gets stale, eventually gets thrown out, and which many people could very much benefit from and build on. So I think it's a wonderful example of the way that a different understanding of what we're doing with research data could transform the daily activities of cultural inquiry. But how it's shared remains a concern, because although projects like NINES and ARC use RDF very effectively to achieve their ends, they use a very simple ontology based in part on Dublin Core. There's no Sparkle endpoint for querying the data, and so inference-based discovery is out, at least for now. Nor is NINES unique. There's very little work on ontology development in the humanities beyond the open annotation collaboration, which moved into the W3C Open Annotation Initiative, which is a great model for annotating, but in terms of domain-specific ontology work, there's very little that's happening. Mostly we have bespoke vocabularies or people just taking bits and pieces from existing ontologies as they see fit. And this is probably for a very good reason, which is that we've been well schooled in the power of classification and its ability to naturalize perspectives and behaviors. Indeed, the very word ontology raises hackles immediately amongst post-structuralists. So projects that are grappling with the question of ontology are few. There's the Info project and the related linked open data enhancer project, but by and large, this is not an area of emphasis within the humanities. So let's turn to the web generally now. We've been doing some work, and this has largely been led by John Simpson, who's been the technical brains behind this, to look at what the web looks like from a humanities perspective as a source for linked open data. And I'm going to try and move through this pretty quickly. These are the tools that we used to essentially try to find out what's happening with ontologies. And what we found is that it doesn't look great. There's less RDF than we think. A lot of it is faux RDF, that when you dig into it turns out to be something else entirely. A lot of it's, you can't get at it, it's not open, and the use of ontologies is pretty poor. So for that last couple of points, I'm going to turn to graphs of the top 12 ontologies that we found. And what you need to be aware of here is that there's a real drop in the size of the y-axis as you move through the graph. So you have about 300,000 uses of RDF schema and RDF syntax namespaces, but once we're down to UMBL, that's about 17,500. And then it drops off even more steeply after that. All of these have 2,000 as their x-axis. So what that means is that a select few ontologies are acquiring the most widespread use on the semantic web, but they don't include the ones that we humanists would think of as the most useful, like friend of a friend or Dublin core. They're in this group. There's a tendency towards very steep drop in the graphs, which signifies the intensive use of a small number of terms from the ontology. And using the Nanjing vocabulary repository, we found that the average semantic web page draws on approximately 6 namespaces for the use of close to 13 terms, with an average of little more than 2 terms per namespace and a wide degree of variance in the distribution. So what that means is that many RDF pages are exhibiting highly selective behavior. They're essentially cherry-picking properties and classes from diverse ontologies, and such behavior is a matter of concern. It suggests that the semantic web is not being used in a way that will allow its inferencing potential to be readily realized, while simultaneously suggesting that many ontologies are not constructed in a generally useful way that would make more of their terms attractive. The tendency of web resources then to adopt only a few terms from one or more ontologies suggests that they're being used to serve, essentially to serve as labels to identify resources for future selection. Certainly a valuable thing, certainly one of the things that the semantic web is supposed to do, but such selectivity may preclude the deeper functionalities that we hoped that it would provide. And Dominic Oldman, a couple of years ago, referred to the danger of producing what he called information jukeboxes, which essentially just reproduce what databases could do anyway. So I'm going to skip through a little bit on friend of a friend and what it does. As we move into thinking about what we need, there's a whole lot. I'm not going to be able to touch on it all, but I will just try and touch on a few things. One of the things that we need in order to get at particularities in the web is to have them there. We need diversity in the data itself. And there have been quite a number of critiques in the last few years of the shortcomings of large data sets that have been used for cultural work. The Culturenomics group, Katie Trumpner has criticized Franco Moretti's work on the British book title for lack of representativeness and lack of comparative data from other countries, but we don't have that data. It's one of the basic problems. So we need greater diversity in our data, and we need more humanities scholars producing it. But we also need to find effective ways of using the increasingly rich data that's pouring into the semantic web. So another danger, particularly given our findings about ontology usage, is that the generalizations required to reconcile big web collections with each other will hinder inquiry into the complexity of cultural artifacts and processes. So for instance, Dublin Core is one of the more widely used ontologies on the web, and if you're using Dublin Core to think about cultural production, you have 2 roles, contributor and creator. You have no way of distinguishing between a translator, an editor, an author, a filmographer. None of that is there. So you have a flattening of relationships that makes inquiry into production impossible. So we need to figure out ways of engaging with ontologies that will allow us to get away from the simple generalization up to a lowest common denominator. So we need not only more diverse data, but also tools that support aligning ontologies in more nuanced ways. And for that, we want something that I would call a difference engine. Sorry, I skipped a few slides here inadvertently. Trying to move us along towards food. We need tools that will allow moderately digitally literate users, so not coders, not programmers, but people who are using the semantic web to see and understand the different approaches to connecting data sets. For instance, the choice of declaring that all editors are creators or that all authors are people could be made apparent in a couple of ways. A tool could present a number of individual data points to highlight the corresponding properties that the ontological choice would entail. For instance, it could show that organizations were now excluded from the class of authors, or that people who are co-authors, once you do the data munging, would not have been alive simultaneously. So to try to show up make more transparent the consequences of bringing the data sets together and what that would mean, and allow people to make intelligent choices about how they were doing that. So it would allow researchers and others engaging with semantic data to work consciously with ontologies to understand their implications and allow them to structure their work so as to capture the differences across data sets that they deem to be relevant. And crucial to this will also be the ability to revise and version ontologies to reflect the changing understanding and practices of particular knowledge communities. So these kinds of difference engines, as I'm calling them, might in the long run mean the difference between encountering Pauline Johnson's posthumous collection of short stories, The Moccasin Maker, with its dated introduction amidst a jumble of disconnected and often conflicting information, as is the case today, and it's on Gutenberg, and finding it with its contents interlinked with other multifaceted web resources in a structured way that allows users to situate the stories and their topics politically and historically. The disparate ontologies and vocabularies used to represent Johnson's complex Mohawk Canadian racial identity, as well as track her changing cultural status as a female writer and performer, could be made transparent and become the basis for bringing in other connections to other materials, embedding Johnson's work in a rich environment of video, images, audio, spatial data that would allow any number of inquiries to proceed from there. Such difference engines are by no means all that is needed, but they will form a key component of a semantic web that can support nuance, allow us to think culture differently, and recognize difference. It will in turn be a better semantic web with a much wider range of applications within and beyond academia, capable of fuller inquiry into the particulars of cultural dynamics, whether we're looking at what's happening with the fate of the book in the electronic age and patterns of consumption. It will allow us to get at reader behavior in a way that we have never been able to get at it before, because that's very, very hard to get in the historical context. But we need that system based on diverse data sets and ontologies that support inquiries into particulars. So the data can come from the open web. One of the things I really like about the knowledge graph is the way that it's got that feedback loop built into it so that you can try and refine what's there. We need systems that incorporate those feedback loops all the time so that we can essentially crowdsource the refinement of the data. Some of it will come from dedicated collections by digital humanists committed to working through a careful modeling of difference and particularity. Some of it will come from crowdsourcing projects like the Link Jazz project, which are built on web communities and powered by citizen scholarship. But much of it can come from the everyday activities of researchers if, but only if, there's infrastructure to support this. So that's what I'm going to spend my last few minutes on. Scholarly infrastructure is changing, if more slowly than the web, to close the gap between producers and consumers. And some projects, such as DM2E, which stands for Digital Manuscripts to Europeana, so it's aligned with the big Europeana project, are doing impressive work in creating virtual research environments for humanities research that support linked data and move us closer to a shared set of big data resources. And I'm also going to talk about the Canadian Writing Research Collaboratory project, which I'm involved in, which is aiming to support the study of writing in and about Canada. It's a combination of a repository with tools for resource production and dissemination. It's designed to get scholars working digitally sooner in the process rather than at the end result, and sharing sooner along the lines of the Alison Booth project in order to benefit themselves from interoperability and interlinking while doing their work. It builds in linked data into its authority management and linking systems and into the production tools that it provides, such as an editor. Both DM2E and Quark are built on the principle that, at least in this early stage, we need dedicated, integrated platforms that embed generic tools for specific activities, such as annotation, into a digital ecosystem that helps manage that data responsibly for scholars. Scholars in my field do not understand what the semantic web is. They're generally hesitant about using digital tools anyway, but they are increasingly convinced of the value of disseminating their work widely. So if we can give them environments in which to work that they can see the payoff for themselves and in the process become schooled in best practices, then everybody wins in the long run. If not, their work is just going to become part of those tidy little static packages that Ian was showing us earlier. What we want is a dynamic digital infrastructure, not only to provide the hardware, but to provide accessible tools, and we need the people power, as people have already been talking about, to provide the support, the training, the mentoring, and the community to allow people to develop the skills that they need. Beyond that, we also need a bigger infrastructure of the kind that the day began by invoking, data centers that can take on long-term preservation and the serving of these objects that are supposed to stay around forever to support the semantic web. If we can get those sorts of robust data centers, that will be a huge win. So we need, finally, in the end, something both like a silo and unlike the traditional data silo, something a little more permeable, a little less rigid, a little less straight, and a little less predictable. This kind of information ecosystem would improve how it's possible to undertake cultural inquiry and other humanities research on the web. It will go a long way, these sorts of technologies, towards what people like David Karger at MIT have been arguing that the public desperately needs in order to manage information better. As he says, we need to make it easy for people to contribute to the web in forms that leverage into more robust, preservable, and usable information for us all to benefit from. That easy part will take a lot of experimentation, a lot of research. We'll need to go into figuring out how best to support this kind of work. So then, big data has real potential for the humanities. There are some real shortcomings in the way it's being used by humanists right now and in the larger linked open data community. We have some hard work to do around tools and infrastructure and on ontologies in order to allow data to scale up without wiping out particularities. Humanities scholars have a vital role to play in this process, given our nuanced understanding of the complex relationships among concepts, languages, and culture, and the dynamic nature of human thought and creativity. We need to be involved for our own sakes, but our involvement stands to significantly improve the semantic web, making it possible to find, analyze, and understand particular webs within an ever-expanding universe. If we do, we will be much better equipped, all of us, to ask tomorrow's questions, and maybe even to answer them. Thank you.
That was a perfect wrap-up to that, because that actually sets things up for this afternoon. So, what we've heard this morning is that there are a lot of people doing some very cool stuff. There is enormous potential within the social sciences and humanities disciplines for transforming our disciplines with big data. But we've also got a long way to go, right? And so, and it is that we exist within a multidisciplinary environment. We've got to reach across boundaries to work with colleagues from computer sciences, from engineering, and even within the disciplines within social science, reach out to industry and into the real world out there that's using this data in order to really move our efforts forward. And so that is the objective then of the afternoon. So lunch is there, that'll fuel the fire, and then we will call you back this afternoon, and we'll start off again with the discussion panel, but then we're going to count on you guys to help us to think about, framing the questions that we've heard about this morning, and how we might make suggestions to SSHRC, and indeed to Western as we move forward as a community, is how we might move forward most effectively.